I'll move forward. I'm sharing my screen. Today we'll discuss one more the extension. Like yesterday we seen the RAM coding, no? So today we'll discuss about FIFO. Okay. So what is this FIFO? We will discuss. Okay. FIFO is nothing but first in first out. Okay. So let us take FIFO. FIFO is nothing but first in first out. Okay. So if you take the FIFO, so this is first in first out. This is one type of queue. Okay. First in first out. First out. Okay. This is one type of queue. Okay. So if you take the FIFO, so this is my FIFO. So you have the inputs. What are the inputs? You have clock and next reset and data in, data underscore in, and write enable, write enable, read enable, write enable signal, read enable signal, and three outputs will be there. So this is my FIFO. One is full, FIFO full, and another one is data underscore out, and next is FIFO empty, FIFO empty. Okay. So if you take these bits, so clock is 1 bit and reset is 1 bit and data underscore in is 8 bit and write enable is 1 bit and read enable is 1 bit and full is also 1 bit and data underscore out is 8 bit and this empty is 1 bit. Okay. So can you say what is the difference between RAM and FIFO? So yesterday we already seen the RAM, no? So what is the difference between RAM and FIFO? Yesterday we already seen about the RAM. Okay. So what is the difference between RAM and FIFO? Can anyone say?
I think we are accessing the memory location sequentially in FIFO.
Related to pins I'm asking.
We don't have any address.
Yeah. In the RAM we have what write underscore address and read underscore address. Okay. But in FIFO you don't have. Okay. So this so we don't have in FIFO we don't have write underscore address and read underscore address. Okay, read underscore address. So that is the difference between RAM and FIFO. So where you are using this FIFO? Okay, any idea where you are using this FIFO? First in first out. Where you are using this FIFO? Suppose
When we want to save the data for some time.
yeah, we want to save the data for some time. Suppose if you take let us take module A. Let us take this is module A, and next one is module B. This is module B. Module B. So these modules, two modules are operating at same frequency, same clock, okay, same clock, and same clock, and these are operating at different frequency. Okay, let us take the frequency of module A is let us take 100 megahertz, and frequency of module B is so 50 megahertz. 50 megahertz. Okay. So this is operated at what? This is let us take this is right frequency. So this is right frequency, and next this one is this is having the high frequency. Okay, this is operating at high frequency. Okay, and next this is read frequency. So this is read frequency, and this one is operating at low frequency. Okay, so so when these two are communicating with each other, so that means there is a chance of data loss. Okay, there is a chance of data loss. Why? Because this is operating at high frequency and this is operating at low frequency. So in order to synchronize this, we need to use, in order to synchronize or in order to avoid the data loss, we need to use the FIFO in between these two modules. So that we can, means FIFO is like it will hold for some time. So it will hold for some time. We can avoid. Okay, to avoid the data loss, we are using this FIFO. Okay, so do you understand where you are using FIFO? Is it fine?
Yes.
Okay, so that means what the FIFO will do? FIFO will hold. So FIFO will hold the data. Okay, the data, whatever the data, for some amount of time. Some amount of time. Okay, so this is nothing but FIFO. Okay, and next you have FIFO full and FIFO empty. Okay, there are like you have three outputs. No, one is FIFO full and data out and empty. Okay, what is the FIFO full and data out? We'll see. Okay, so let us take FIFO full. So full. So FIFO full. If you take FIFO full, this indicates that FIFO is full. This indicate that FIFO. So whatever the FIFO is there, FIFO is full. Okay, FIFO is full, and so when FIFO is full, we can't do write operation. So already the FIFO is full. Okay, so there is no more locations available in the FIFO, so that we can't do the write operation. Write operation. Okay, we can't do the write operation. And empty. Empty means what? So before writing the data into the FIFO will be empty. Okay, when the FIFO will be empty, so what happens? FIFO will be empty means that means we can't do the read operation. We can't do the read operation. We can't do the read operation. Okay, so this is nothing but FIFO full and empty. Okay, so uh, so here if you see, so we'll see the coding part. Okay, design code, RTL code for FIFO. RTL code for FIFO. So I'm writing module FIFO. I need to declare the input and output. Input clock, input clock, reset, and write underscore enable, comma, read underscore enable. Okay, and so input that is 7 down to 0, data underscore in, and next output. Mm, what are the output data? That is one is full and next is empty, and next is 8 bits of data, 7 down to 0. So empty, full, and I need to declare one more time, that is output. Okay, uh, output 7 down to 0, data underscore out. So like this you need to represent. Okay, and last class we already seen how to create the memory. So that this is nothing but, let us take you have FIFO of depth 8 locations and width is also 8 locations. Okay, I'm developing a FIFO with 8 location depth and 8 location width. Okay, so I need to develop the memory. Okay, so how to develop the memory? Ridge, that is 7 down to 0, mem of, okay, 7 down to 0. Okay, with the help of this arrays and memories, I'm making the memory. Okay, this is nothing but memory. Okay, and next what I am doing means I'm initializing two pointers. Okay, those are nothing but write pointer and read pointer. Okay, so I'm initializing, that is write pointer. So reg 2 down to 0, this is write pointer. Okay, write pointer, and next reg 2 down to 0, and another one is I'm initializing. So I'm initializing write pointer to what means I'm initializing to uh, one second. Yeah, initializing to that is 3-tick binary 000. Okay, and range 2 down to 0, read underscore pointer, that I am initializing to 3-tick binary 000. Okay, so that means here if you have a FIFO, this is nothing but my FIFO. Okay, so FIFO have how many locations? So total 8 locations are there, 0, 1 up to so on and up to 7. Okay, so that means here what I am doing means I am initializing this right pointer to this 0. Okay, this is point to this one, right pointer to 0 and read pointer to 0. Okay, so this is nothing but right underscore pointer, and this is nothing but read underscore pointer. Okay, so whenever like I'm doing the right operation, right pointer will be incremented. Okay, whenever I'm doing the read operation, read pointer will be incremented. Okay, every time when I am doing write operation, write pointer will be incremented, and when I am doing read pointer will be incremented. For that, I am initializing two intermediate variables, that is write pointer and read pointer. Okay, next I am initializing integer I. Okay, integer I. Okay, so I am initializing one second. So I am initializing integer I. Okay, so integer I, one second. So yeah, integer I. Okay, after that, so integer I, always at the rate passage of clock, always at the rate passage of clock, begin if reset. Okay, so if reset, what I am doing, begin I'm clearing the memory location. That means I'm using for loop for I equal to 0, I is less than 8, and I equal to I plus 1. Okay, so I equal to I plus 1, so that is I plus 1, I can use I plus 1, mem of I. Okay, that is non-blocking with 0. Okay, and end. Okay, I am clearing the, so that is here I am clearing the content of all the locations. Okay, clearing the content of all the locations, all the locations. Okay, locations. Okay, else if, okay, else if so if write enable, if write enable equal to 1. Okay, begin mem of right pointer. In this right pointer, I am loading the data. What is the data? 8 bit of data underscore in. Okay, uh, after that, every time when I am doing the right operation, what I need to do, I need to increment the right pointer. So right pointer, that is non-blocking with right pointer plus 1, right pointer plus 1, and enter. Okay, so this is nothing but what operation? This is nothing but my write operation. Write operation. Okay, this is nothing but my write operation. Okay, and coming to the read operation. So read operation. If you see the read operation, is this write operation is fine? Any doubts or queries in this? Shall I move forward?
Yes.
Okay. So next, coming to the read operation. Okay. So if you see the read operation, so always at the rate passage of clock, begin if reset, data underscore out, that is non-blocking with what? 0. Okay, else if read underscore enable, if read underscore enable equal to 1, begin begin uh, so data underscore out, so that is So that is yeah, I think here one more end will be there. So for the begin, we need to end. Here one more end will be there. Here one more end. And next, so begin data out is initialized to 0. Okay. Uh, if reset data out is initialized to 0, if that, one second. Here, if it is read enable, okay. So data out is initialized to mem of read pointer, read underscore pointer, okay, read underscore pointer. And after that, after read operation, what I need to do? Read underscore pointer, that is I'm initializing with read underscore pointer plus 1, okay. I need to increment, okay. And next end and end module, end, okay. This is for this end, and begin is there, no, that is that end, okay. So this is read operation, okay. This is read operation, okay. Next, I need to check for what? Empty. Okay, I need to check for empty. Okay, how to check for empty? So empty means, suppose like uh, so here this is my FIFO. This is my FIFO. So empty logic. So if you see the empty logic, this is empty logic. How to develop the empty logic? So if you see the FIFO, here you have some read pointer. Okay, here you have read pointer. Okay, so somewhere here you have write pointer, read pointer and write pointer. Okay, so what happening? Suppose FIFO is reading the data, it is coming here, and during this position, read pointer equal to what? Write pointer. Okay, write pointer equal to what? Read pointer. Okay, so when write pointer equal to read pointer, okay, that means when write pointer that is equal to read pointer, okay, read pointer, then we can say that FIFO is said to be empty. FIFO is empty. FIFO is empty. Okay, so how to declare? Like assign empty, that is equal to, I think you are using behavioral modeling means this one you need to declare with range data type. Okay. So output you are using out, no. One second. Um, yeah, data out you are using, no. So you are using in the behavioral modeling. So this you need to declare with range data type. Okay. So output range need to declare. Okay. So output range data out. Okay. And assign empty equal to what? Empty equal to, so I'm using ternary operator. Right pointer, right underscore pointer, that is equal to read underscore pointer. So if condition is satisfying, that is equal to 1, otherwise 0. Okay, ternary operator I am using. Okay, so this is the logic for what? FIFO empty. Okay, and coming to the FIFO full. Okay, FIFO full means so here, suppose FIFO full means you have FIFO. So here somewhere here you have read pointer. So right pointer, we are doing the right operation. Okay, so total 8 locations are there. So you are doing the right operation. Here at the last, you are doing the right pointer is here. Okay, you done all the 8 locations. You done the right operation. Okay, so that means here what is the right pointer value? 1111. Okay, so 1111 when you are adding means you are incrementing. Okay, so when incrementing, what you are getting? That is you are getting 0, 0, 0, and carry. You are getting carry 1. Okay. So carry 1 means this you discard. This you discard. Okay. So that means what you are getting. So that means so here you are getting something. You done read pointer also. Okay. So that means uh, so when you are adding this value, it becomes 0. No. So I will develop the logic, that is assign. Okay, this is full logic. Full logic. Assign, assign. Uh, that is full. Okay, full. That is equal to write pointer plus 1 tick binary 1, that is equal to read pointer, that is equal to read pointer. Okay, then if it is equal to 1, then FIFO is full, otherwise FIFO is empty. FIFO is like some value is there. Okay, so this is the logic for FIFO full. Okay, and next end module. Okay, so you need to develop the logic for FIFO empty and FIFO full. FIFO, what is FIFO empty? So assign empty equal to write pointer equal to read pointer, that is equal to, when write pointer equal to read pointer, then FIFO is said to be empty. Okay, so that means you are using a conditional operator or ternary operator. Here also I am developing logic for full. Okay, assign full write pointer plus 1 tick binary 1 equal to read pointer, that is 1 tick binary when you are adding, that is equal to when you are getting read pointer, then FIFO is said to be full. Okay, this is the logic for FIFO. Okay, is this fine FIFO code? Any doubts or queries? Shall I move forward?
We need to use this empty and full while writing and reading also, right?
Yeah, yes. We need to check for FIFO empty and full also. Okay.
So can you, in our logic, right, in our always block, so while reading, we are only checking read enable, right? So
This FIFO full or empty, we are checking for right, means here in the behavioral modeling, I am not checking. After the behavioral modeling, I am checking the condition for empty and full. These are the conditions for empty and full.
yeah, that I understood. Like, so where we are using this one? I mean, if it is full, we cannot write, right? So while writing, we need to have a check for that also, right?
Yeah. Writing, we need to check this also. So as this is concurrent, no, concurrent means what? When you are doing write operation, so it will come to this assign statement, and it will check for the condition. So when it is not full only, it will do the write operation. Otherwise, it will not do. You will get empty condition.
Can you go up? That right block will be there, right? So this one. Then. So we should give a check, right? Else if write enable and empty or something we need to give, right? Not full or something.
No need to give here. Here we are doing write operation, no.
Yeah, but if it is full, how can we tell like it is full and we cannot write? So that condition where we are giving.
Okay. Okay. Mhm. Okay. We need to check in the write operation and read operation also. So that means here you need to write. So assign we can't write in the behavioral modeling. So we can write empty equal to, or otherwise we need to represent this with range data type, full or range. Or otherwise this is the concurrent language. No, that means this block, and this block will be executed parallelly. Every time write operation means what? So right when you are doing write operation, so parallelly it will check for the full condition and empty condition. As I said
Yeah,
during the behavioral modeling, no.
yeah,
So
that
this
is
is
correct.
uh,
My query is like, yeah, it will check concurrently, same
uh,
one, that is
uh,
correct.
uh,
But
uh,
while writing, right,
uh,
see, like, even though our full variable is assigned to one,
mm.
here we are not giving any check, right? Even though it is full, then it will start writing, right? If write enable is equal to one in all this block.
Yeah. Actually, like so parallelly it will check for the full condition only. Why? Because parallelly this is one block. This is one block. Always is one block, and this is read operation is one block. Assign is one block, and this assign full is one block, and assign empty is one block. So that means parallelly when it is executing, it will check for full and empty only. First it will check for full and empty only. Then only this will be executed. Uh,
Yeah,
Understood?
that I understood actually. I mean, even though
Uh,
we are checking for full and empty, but
uh, uh,
in while write in a write logic, right, we are not
uh.
using that full and empty
We are not
to
using. We are
qualify
not
the right.
using. Why? Because parallelly it will execute now. So concurrently, parallelly it will execute means always when it is executing, it will check for full and empty only, no? So why we need to check for the condition in write operation and read operation? That is my question.
Yeah, so parallel it will check, for example, we have written into the full location and
Uh,
full is set to 1.
uh,
So then even though we are trying to write, it will
uh,
again start writing, right? It will overwrite the data, right? Because we are not even using that full logic inside write statement, right? It will
yes.
just check for this address is, I mean, sorry, that write is 1 or write enable is 1 or
Right enable is one. Yeah, 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 yeah. So before this, like parallel, it will. So my answer is like parallel it will execute means parallel it will check for right condition. Okay, the parallel it will check for full and empty condition. So why we need to again write in this always block is my question. Did you understood?
Yeah, that's kind of my question also. Like, so where we are using
Uh,
this full and right? So, like, you're writing that in, you're writing, if write enable, you're writing some data,
uh,
and that concurrently we're checking if it is empty or full.
yes,
After
yes, yes.
checking, then where you're using this empty and full. You're not even
Empty and
using any.
empty and full, that will be first it will be checked this assign empty and full. So if this condition is if empty equal to 0 only, it will do the like right operation. When full
Yeah,
equal
but
to 0
where we are
only, it
checking
will do
that, yeah, but that
parallelly
check,
we are checking. Parallelly the code is checking parallelly. Parallelly code is checking. Parallelly this block and this block and this block will be executed parallelly, no?
okay, yeah.
Understood. Understood. So
No, like my question is like while writing,
hmm.
else if write enable and not equal to full,
So
that should be
yeah,
we
understood
should
your
give that one,
answer.
right?
That means this condition we need to check here. You are understood your question. Your question is why you are not writing this empty condition and full condition within this block. That is your question, no?
No, my question is like why we are not using. So we have sent it empty and full.
Uh,
We have given a logic, but why we are not using this empty and full as a check before writing or reading?
yeah, before writing or reading. Yeah, yeah, yeah. Understood. That I will check and I will tell you. But as per your question, my understanding is as this is parallel logic in the behavioral modeling, we checked with different blocks. No, all blocks will be executed parallelly. So parallelly means parallelly it will check for condition. So after condition is satisfying only, then this will be right operation will be done. That is my answer. But anyway, I will check about this. Okay, your question. I'll let you know. Okay, okay. So we'll see the coding part. 1 second. 1 second. Vivado is opening. So this is my FIFO code. First, so here if you see, so I'm creating module FIFO input clock, input reset underscore n, input write enable, input read enable, input 7 down to 0 data in, and output range 7 down to 0 data out, output full, output empty. So I'm making this range 7 down to 0, mem of 7 down to 0. I'm creating the memory. After that, I'm initializing write pointer with 2 down to 0 and read pointer with 2 down to 0, and this is write operation. So integer I, integer I always at the rate passage of clock or negate of reset. I am checking for asynchronous active low reset begin. If not of reset, okay, if reset equal to 0, right pointer I am initializing to what 0, okay, and for I equal to 0, I is less than 8 and I equal to I plus 1. Mem of I equal to what 8 tick binary 0. I am clearing the content of all the locations. Yeah, so you are, yeah, yes, and else if, okay, here, yeah, so see here, so I think we can check here itself. I think your doubt is clear. If write enable and not of full, how you understood, like,
Yes.
okay, if write enable and not of full begin, we write memory write pointer equal to what, so here itself we need to check the full operation, okay. So if full equal to 0 only, then we can do the write operation. Memory of write pointer equal to, that is data in, and after that I am incrementing the data pointer, okay. This is nothing but write operation, okay. And read operation means always at the rate passage of clock or negate of reset begin. If not of reset begin, I am clearing the read pointer. Okay, read pointer equal to 0 and data out is also I am clearing with uh, ATIC binary 0. And else if, here I need to check for what, for read pointer I need to check for empty. Okay, if read underscore enable and empty equal to 0 only, this it will do the read operation. Okay, suppose if it is if it is empty, no data is there, I can't do the read operation. No other data is there, so I can't do the read operation. So that's why when empty equal to, so that means empty equal to 1, we can't do the read operation. If empty equal to 0 means some data is there, I can read the, so it can read the data. FIFO can read the data. So read underscore enable and not of empty begin data underscore out equal to mem of read pointer. After read operation, I need to increment. Okay, read pointer equal to read pointer plus one tick binary 1 end and end module, and checking for the status flag. So the status flag I told you, no. So you are checking for full and empty. That is right pointer, that is right pointer equal to right pointer plus that is full equal to right pointer plus one tick binary 1, that is equal to read pointer, then this is the full condition. Assign empty equal to what, right pointer equal to read pointer. Like this also you can use checking for the full and empty and end module. Is this code is fine? Any doubts or queries? I think your doubt is clear, I think so.
Yes.
So that means we need to declare here within the always block only. We need to check for full condition for write operation and empty condition for read operation. Okay. And coming to the test bench, this is the test bench. Okay. So if it is a test bench, so clock reset underscore n, write enable and read enable, and data underscore n we need to declare with range data type, and data out full and empty you need to declare with write data type, and you need to instantiate your design. What is your design? FIFO design under test, and this is instantiation by name. Okay, so whatever the variables outside the bracket are design inputs and outputs, and whatever the variables inside the bracket are nothing but test bench variables. And next you need to generate the clock, always hash by clock equal to not of clock, and you need to initialize the clock, clock equal to 0 reset underscore, initialize the range variables. Okay, so clock equal to 0 reset underscore n equal to 0, write enable equal to 0, read enable equal to 0, data underscore n equal to 0. Okay, after 20 time units I am making deassetting the reset. Okay, repeat 8, repeat is one keyword. I want to repeat for how many times means 8 clock pulses, 8 times I need to do repeat at the rate passage of clock. This will should be done at the passage of clock only. So write enable equal to 1 means what, it is doing the write operation. So I am making read enable equal to 0. Okay, so data, so every time data will be incremented. So data underscore in equal to data underscore in plus ATIC H01 and end. Okay, this is write operation. And Here when write enable equal to 0, then what happens, FIFO will be full at the passage of clock. After 8 bits of data, after writing 8 bits of data, FIFO will be full. Okay. So during this stage, FIFO will be full, and this is read operation in empty. So repeat for 8 times at the rate passage of clock. Read enable equal to 1 and write enable equal to 0, and at the rate passage of clock, read enable equal to 0 means FIFO should be empty here. Okay. And hash 20 dollar finish and I want to like dollar monitor means in the Verilog event scheduler we already seen. So like it will be displayed in the postpone region. So whatever the change in the variables, then this will display. Dollar monitor is a system task. Whatever the change in this variable, there is a change in these variables, then it will display end and end module. Okay. This is the code, and I want to see the simulation part. Okay. So if you see the elaborated design, just run the elaborated design. So this is the tool is converted your FIFO into this like this. Okay. And simulation, run simulation. So we can see in the TCL console also. So here write enable equal to 1 means till FIFO is full equal to 0, it is doing write operation. So when data in equal to 1, FIFO becomes full. Okay. After that, so here it is read enable becomes 1, and it is doing read operation. Okay. It is doing read operation. After that, empty becomes 1. Okay. Read operation is after 8 bits of data, empty equal to 1. You can see in the this waveform also. So here first so reset underscore n. When reset equal to here when reset equal to 0, so here that out equal to 0 only. Okay. And when reset equal to 1 only during this passage of clock, so what happening, write enable becomes 1, so it will do the write operation. Okay. So 0 1 2 3 4 5 6 7. Okay, like this 7. Okay. So after this what happens, 8 bits of data is written into data underscore in. Okay. After that, read underscore enable becomes 1. Okay. Now write underscore enable becomes 0. So it will do read operation. Okay. It will do read operation. So that is coming at the so during this after write operation, full becomes 1. Okay. FIFO will be full becomes 1. Okay. And after this read operation is happening. So during this read operation, read underscore enable becomes 1, and it is doing the read operation what is with the data is available at the data out signal, and after reading 7 bits of data, empty becomes 1. Okay. Empty becomes 1 means what, so we can't read the data. So when empty becomes 1, we can't read the data. Okay. So read operation is completed after 8 bits of data. Read operation is completed. So this is how you need to check for FIFO. Is it fine?
Yes.
Okay. Parameter also. This is FIFO by using parameter. So last class we already seen the parameter. Based on the parameter, like I'm giving data width as 8, depth as 8, and address is dollar log to depth. Like this I'm giving. Okay, address log to. C log to depth, and I'm declaring these inputs and creating the memory. Address width minus 1 is to 0. That is, if you are taking address width as what 8 means 7 down to 0. Sorry, this is address width is how much? 3 bits now. So 3 down to 0, right pointer, and 3 down to 0, right pointer, count. Same thing I need to do. Just with the help of parameter only I need to use. Okay. And coming to the test bench. So same thing. Test bench you need to declare the parameter, and you need to declare the internal variables. This clock reset, write underscore enable, read underscore enable, data underscore in, and data underscore. These with the reg data type, and remaining with y data type. I'm declaring instantiating. This is instantiating. FIFO param hash dot data width data underscore data width depth and dut. So like this instantiation connection by name, generating the clock, and I'm initializing the range variables and applying the reset for 20 time minutes, release the reset. Okay. And by using for loop, I'm doing the write operation and read operation. Okay. I'm checking for full condition and display empty condition. Okay. So like this, you can see using parameter also. So if you want to see the parameter, set as stop and run simulation, run behavioral simulation, run behavioral simulation. We can see the output fit to page. Okay. So here it is doing write operation. So when write operation is happening, write enable equal to 1, and after that full becomes 1, and here read operation means read enable becomes 1, and it is doing read operation. After read operation, empty becomes 1. Okay. So this is the code simulation related to the FIFO using parameter. Is it fine? Any doubts or queries related to FIFO?
No.
Okay. What about others? Okay. Okay. So next, so this is about FIFO, and next is we will see the FIFO depth calculations. Okay, this is also one of the interview question they will ask how to calculate the depth. Okay, FIFO depth calculations. Yeah, FIFO depth calculations. Okay, so we have some cases. So we will take. I will take one case one. Case one. You have module A, and this is module B, module A and module B. So module A is connecting with module B, and module A is operating at 80 megahertz, and so this is write frequency, and module B is operating at 50 megahertz. This is read frequency, read frequency. Okay, and so here FA equal to the given the data 80 megahertz, and FB equal to 50 megahertz, 50 megahertz, and how many that is you need to calculate the FIFO depth calculations. Okay, so FIFO depth we need to calculate FIFO. What is the FIFO depth? Okay, so FIFO depth. Okay, total data items you are transmitting, that is D equal to 120. Total data items you are transmitting D equal to 120. So here how to calculate means, suppose time taken for writing one bit of data is nothing but TA. Okay, so this is time taken for writing one data item, for writing one data item. Okay, so data item. data item. So TA equal to 1 by 80 megahertz. 1 by 80 megahertz. This is how much you are getting. Can you tell me? 1 by 80 megahertz how much? 12.5 nanoseconds. Okay, 12.5 nanoseconds you are getting. Okay, and next time taken for writing. So that is, this is time taken for writing one data item. Time taken. So time taken for writing 120 data items. 120 data items. Okay, so data items is given in the problem as 120. Okay, so that is 12.5 nanoseconds into 120 data items. So that this is equal to, you are getting around 1500 nanoseconds. 1500 nanoseconds. Okay, so next TB for reading. One data item. One data item is how much? So one data item is TB equal to 1 by 50 megahertz. So this is how much? 20 nanoseconds. 20 nanoseconds. Okay. So that means 20 nanoseconds will take for reading. That is one data item. 1500 nanoseconds will take how many data items? X data item. So here x equal to how much? X equal to 1500 nanoseconds divided by 20 nanoseconds. This is equal to, you are getting 75. Okay, you are getting 75. Okay, so data item, this is nothing but, so this is the data items which can be read, which can be read 1500 nanoseconds. Okay, 1500 nanoseconds. So what is the total depth calculation? 120 minus 75. So 120 minus 75 means 45 data items. Okay, so data items are missing. 45 data items. Okay, data items are missing. Okay, are missing. This is nothing but this much of data will be lost. So how much of the FIFO depth? So the FIFO depth, we need to design a FIFO with this depth. Okay, depth is how much? 45 locations. 45 locations. Did you understood the case one, or shall I explain one more time?
Understood.
Okay, yeah. So next, let us take case two. Case two. Case two. They given FA equal to 80 megahertz and FB equal to 50 megahertz, and data items to send from module A to module B is 120, and they given the ideal cycle ideal cycle between consecutive write is 1. Ideal cycle between consecutive read is 3. Consecutive write is 1 and read is 3. Okay, so write is 1, read is 3 means what? So like consecutive cycles. So suppose this is write cycle. So here, so how it will be there? So here there is a write operation. So here there is a write operation. So here write operation will be there. Okay, and so this is one clock cycle. This is one clock cycle. So here next clock cycle this will be idle. Okay, and after that again next clock cycle, then there is a write operation like this. Okay, again there is idle. Next, again here there is a write operation. Like this it will do. Okay, this is nothing but ideal cycle between consecutive write cycle is how much? 1. Okay, consecutive write cycle is 1. Okay, if it is a read cycle, ideal cycle between the consecutive read is 3 means what? So here you have like these are the read cycle. These are the read cycle. So here, so ideal cycle. So that means suppose here there is a read cycle. So after consecutive, how many cycles? Consecutive 3 cycles. So 3 cycles. There is a read operation. Okay. So there is ideal cycle, and here there is a ideal cycle. Here there is ideal cycle. Okay. After this, there is a read cycle. After this, there is a read cycle. Okay. So that means here here if you see, this is for every 2 clock cycles. Why not? One write operation is happening now. For every 2 clock cycles, one write operation is happening. Write operation. Okay, write operation is happening. Here what happens? Here for every for every, so this is for every 4 clock cycles, one read operation is happening. One read operation is happening. Okay, is happening. So here that means writing. So what is the writing frequency? 80, no? So 80 means how to calculate? That is for writing TA. TA equal to how much? That is 1 by 80 into every 2 clock cycles write operation is happening. Okay, into 2. So into 2 means how much you are getting? 25 nanoseconds. Okay. Uh, so that means TA for writing 120 data items. 120 data items. How much? 25 into 120. So 25 into 120 means you are getting around 3000 nanoseconds. 3000 nanoseconds. Okay. TB equal to how much? For every how many clock cycles read operation is happening? Four read cycle. Okay, four clock cycles read operation is happening into 4. So this you are getting 80 nanoseconds. Okay, 80 nanoseconds. So 80 nanoseconds, one read operation is happening. Okay, 300 nanoseconds, how many read operations? 3000 nanoseconds, how many read operation is happening? Okay, so here x equal to what? X equal to 3000 nanoseconds divided by 80 nanoseconds. This is 37.5. 37.5 means nearly approximately you need to approximate to 37 data items. 37 data items. Okay, what is the depth of FIFO? So depth of FIFO, that is equal to 120 minus 37. So this is 83 locations. 83 locations depth of the FIFO is required. Is it fine? This case 2 is fine. Any doubts or queries?
No.
Okay. Next case 3. So case 3, they given F equal to 80 megahertz and FB equal to 50 megahertz and D equal to 120 data items. Duty cycle of write enable equal to 50%, and duty cycle of read enable equal to 25%. So means what is duty cycle? What is duty cycle? T on by T on plus T off. Okay. So duty cycle, this is on for 50 times. So that is 50%. So 50% means what? So 50% duty cycle means. So here you are getting this is so for every so how much clock cycle it is every so you are getting duty cycle. This is equal to 1 by 2 you are getting, and here you are getting 1 by 4. Okay. So same for every 2 clock cycles, one write operation is happening. One write operation. Okay. For every 4 clock cycles, one read operation. Okay, one read operation. This is same as what? Cached. Okay, this is same as cached we discussed. Cached depth calculation. Is it fine case 3 with respect to duty cycle?
Yes.
Okay. And next case 4. Case 4. Case 4. FA equal to 30 megahertz. FB equal to 50 megahertz. D equal to what? 120 data cycles. So how we can do? Is FIFO is required?
No.
No. Why? Because writing writing is slower than writing is slower than
Reading.
reading. Writing is slower than the reading. FIFO is not required. Okay. FIFO is not required. Okay. Not required. Okay. 1 second. FIFO is not required. Okay. Yeah. Case 5 we'll see. Case 5. FA equal to 30 megahertz. FB equal to 50 megahertz. D equal to 120 depth 120 cycles. Okay. And next so ideal cycle between consecutive write cycle. Ideal cycle between consecutive write cycle equal to 1. Ideal cycle between consecutive read cycle equal to 3. Okay. Here what you need to do? TA equal to, for every 2 cycle write operation is happening, 2 into 1 by 30 megahertz. Okay. 30 megahertz. This is equal to 66.6 nanoseconds. And TB. So TB equal to 4 into 1 by 50 megahertz. So this is 80 nanoseconds. 80 nanoseconds. So 66
3,
point.
right? 3
1
or
second.
4?
What? This is actually previously we already seen, no.
No,
If
no. I
it is
mean,
3,
ideal cycle between read cycle is 3, right? So
yeah, 3 means read operation is happening for every 4 clock cycles, no.
Yeah, correct. Okay, see.
For every clock cycles, write operation is happening. For every
Yes,
4
yes.
clock cycles, read operation is happening. That's why I multiplied with 4. Okay. And next, so that is 66.667 into 120. You are getting 8,000 nanoseconds. Okay. So 8,000 divided by 80, the x equal to, okay, this is equal to 100, you are getting 100. So depth, that is the 120 minus 100, this is the 20 locations, this is the required FIFO depth required. Is it fine? Case 5.
Yes, yes.
Okay. And case 6, case 6, FA equal to 50 megahertz and FB equal to 50 megahertz, and idle right cycle, this is equal to 1, and idle read cycle this is equal to 3. So here that is TA equal to T into both right cycle and right frequency and read frequency, both are same only, 50 megahertz. Okay. So 2 into 1 by 50 megahertz means you are getting 40 nanoseconds. And next, TB equal to uh, TB equal to 4 into 1 by 50 megahertz. You are getting 80 nanoseconds. 80 nanoseconds. So 40 into 120. So you are getting 480 nanoseconds per x equal to and 480 4800. Sorry, this is not 480, 4800. You are getting 4800 nanoseconds. 4800 divided by 80. Okay, so 0 0 cancel. You are getting 60. 60. So how much of the depth calculation? 20 minus 60. This is equal to 60 locations of FIFO is required. Locations of FIFO is required. So this is about the FIFO depth calculations. Is it fine?
Yes,
You understood? Okay.
yes.
Yeah. So in the next class, we see about the FSMs, finite state machines state diagram. Okay.